So what I want to do in this video is derive an integral representation for the Hurwitz Zeta function. And I'll remind you that the Hurwitz Zeta function is given by this. It's given as zeta of SNQ is equal to, and then something that looks a little bit like our normal zeta function, except that we're shifting the denominator by this number q. And so, for example, if we set q equal to 1, then we get back the normal zeta function, the normal Riemann zeta function. Okay, so that's our Hurwitz zeta function. The integral property that we want to derive is this. It's integral 0 to infinity x to the s minus 1 e to the minus qx all over 1 minus e to the minus x is equal to our Hurwitz zeta and our gamma of s. And the way that we derive this is going to be very similar to how we derive the integral representation for the zeta function. So I would encourage you to first try out on your own, see if you can start with this integral and work your way over to this right hand side, and then come back and see how I actually do it. But let's get started. So what am I going to do? I'm going to start with this integral, and maybe I should put a dx on here. And I'm going to work my way to the right hand side. So we see this 1 over 1 minus e to the minus x here in the denominator, and we know that this right here, sort of anticipating that we want to get this into the form over here, we know that this right here has a nice form as a geometric series. And that geometric series goes from 0 to infinity, and it's e to the minus n x. All right. So that means that we can rewrite this integral right up here using this, and we end up with something that looks like, what, integral 0 to infinity x to the s minus 1 e to the minus qx times, and then our series, our sum from n equals 0 to infinity e to the minus nx dx. All right, so this is our integral, and now we can just do the normal thing. This n is independent of this x, so we can pull out the sum. So we have sum n equals 0 to infinity, and then we have integral 0 to infinity x to the s minus 1 e to the, and then I'll write this like this, minus x q plus n dx. Okay, that's fine. But now let's start thinking about this, right? We know that this right-hand side needs to start looking like this right-hand side up here. And we have a sum, which is good for our Hurwitz zeta. And so that suggests that what we want to do is get this integral right here in the form of a gamma function. And we were almost already there, right? We have this e to the minus x with this extra factor up here. And so that suggests that what we need to do now is use a change of variables. And that change of variables should look like u equaling to x q plus n, because that'll fix this exponential term right here to look like what it should for the gamma function. So we have this q plus n. So let's plug it in and see what happens. So this guy right here, and I'll change colors. This ultimately gets us down to this, where we have sum n equals 0 to infinity integral, and now let's be careful. So x is equal to u over q plus n, so we're going to have u to the s minus 1 over q plus n to the s minus 1. Then we're going to have our e to the minus u, how we set it up, and then our dx is equal to what? It's equal to du over q plus n. Okay, great. And now we've just about got it, right? We have this q plus n in the denominator here, which is independent of this integral. And that means that we can pull it out, and what we're left with is what? Sum from n equals 0 to infinity. We can pull out a factor of q plus n to the s minus 1, so that's going to be 1 over q plus n to the s times, and then we have our integral. 0 to infinity, u to the s minus 1, e to the minus u du. And then you see this is just another way of saying exactly what we wanted to have right up here on our right hand side. This is exactly equal to our Hurwitz zeta of s and q multiplied by the gamma function. And so we've done it. we've started with this integral over here on the left-hand side, and by forcing things into this form right here, we were able to prove this property. And so maybe you're starting to see, and this may become evident as we do more of this type of stuff, but there's a whole class of integrals that kind of look like this, which when you solve them end up being in terms of some zeta function times the gamma function, or something that is a generalization of the zeta function. And so here we have something just like that, right? If we would have had this integrand looking a little bit different, we just get the zeta function. But now that we've generalized it a little bit, we add this q, we get a more general integral right here. And then, when q is equal to 1, this is just the zeta function property that we're familiar with. But now we've generalized it, so we have to use a more general zeta function. And we'll see that as we start generalizing our zeta functions more and more, we'll get more and more generalized integrals that we can solve. And so that's a really nice thing that you get by generalizing the zeta function, is you can solve a whole bunch of otherwise really hard integrals. But I think I'll stop there, and I hope to see you in the next video.